I've been waiting for months to report on 1 month's activities in which I could focus on the parts I enjoyed the most personally, and that's development. Well, all the fundraising efforts in the past have finally paid off both literally and figuratively, because the time has come and June was about nothing but development. Since me and Aljaž are both working remotely for the time being, the biggest win of the month has to be my trip to the Netherlands, where we spent the weekend together talking about where we currently are with the project and where we want to take it both in the next couple of months, but equally important, in the next couple of years. So where are we in the end of June in terms of progress? Well, on Aljaž's side, he finally received these super cute and tiny testing boards for M.2 latches that he designed and then ordered with the sponsor of today's video, PCBway. You see, in order for the final customers to have an easy way to add or remove M.2 cards, and we'll get to their specification shortly, we needed to find a simple latching mechanism that A, wouldn't be too expensive, B, would be modular enough to support different M.2 card lengths such as 30, 42 and 80 millimeters, and C, well, would be of sufficiently high quality. In this regard, I'm happy to report that the ones that Aljaž found by a Taiwanese company called 5TK fit all the requirements perfectly and will very likely be part of the final product. Second good news from his side is also the fact that the schematics are nearly done. We were hoping they will be completely finished by the end of June, but we encountered one simple and one not so simple issue. Let's talk about the simple one first, because it's really not an issue, it's just that it requires a bit more time to be worked on, and that is power supplies. In the context of embedded systems, power supplies are not your typical big metal boxes that you plug into the device, but rather are tiny chips on the PCB that make sure enough current is provided at a given voltage. To the devices that operate at set voltage, that is. For example, some devices require 5 volts, others require 3.3, 2.5, 1.8 or even 0.9 volts. Some more complex ones, like the CPU, even require a combination of voltages. But here's the trick. When the device is powered up, the sequence of power supplies being turned on, or to put it differently, in what order each voltage is provided to the CPU, becomes very important. You can't just turn them all on at the same time and hope for the best. For example, in order for the CPU to access RAM, the correct voltage that RAM operates at needs to be supplied first, so that when the CPU gets its operating voltage, the RAM is already powered up and accessible. Obviously, this is an oversimplified example, but it felt important for me to bring it up, not because it would be any kind of technical limitation, but because I'd like to outline its relation to price. You see, there are two ways to skin this cat. Let's assume there will be around 10 power supplies on our board. The way that the development board we're using to test the CPU features does it is that it has a dedicated chip that is called a PMIC, or Power Management IC. It's sort of a supervisor chip of the power supplies, so to speak, and its main function is to turn all of them in the correct sequence. However, compared to the power supplies themselves that cost less than $1 each, it's a fairly expensive chip costing around $5. So Ken, the hardware developer that helps us develop the router, came up with the idea to not include the power management chip in the first place. This is possible because many power supplies come with a special pin that is called Power Good, which translates to, hey, I'm up. And if we route this pin to the power supply that's next in the power sequence, it'll turn that one on. Basically, with the correct choice of power supply chips, we get rid of the power management chip and thus both save some money and also simplify the design of the board a little bit. And now let's talk about the bigger issue, and that is the main storage of the device. Since the CPU comes with an integrated flash controller, the first and most obvious choice was of course to attach NAND chips directly to it, which we've done at the planning phase, but missed one very important detail, and that detail turned out to be a showstopper. See, all the NAND chips on the market that come in quantities bigger than around 8 gigabytes work at 1.2 volts, whereas the controller that's on our CPU operates at 1.8, which pretty much means we can't use it. or rather, we can't use high-capacity NAND chips with our CPU. Now, of course, there are plenty of other buses we can put our boot drive on, but unfortunately, every single one of them comes with a drawback, so let's briefly talk about all of them. First, and the one that was recommended to us by the distributor, was to use an eMMC chip, the same one as you can find in an SD card, for example. And here's the important part. eMMC chips attach to a bus called SDIO, one of which we do have on our CPU, but because we want to support M.2 Wi-Fi cards, many of them use this very same bus, so we also need to route it to the M.2 port. And because this bus can't be used by more devices simultaneously, we need to use something called a multiplexer or a muxer, which is a chip that behaves sort of like a three-way crossroads with a traffic cop on it. Only traffic from one chip can flow back and forth between the chip and the CPU at any given time. So this basically means that the bandwidth of each depends on, well, traffic congestion. Now, we're talking about a router here, so read and write speeds aren't really that important. So it's not an issue of performance, but one of board complexity. The second option, if you remember from one of my previous videos, I explained that the second SerDes block also has a SATA interface next to one PCIe 3 lane, one PCIe 1 lane, and one SGMII lane. It also has a bunch of other possible combinations, but each of them, except the last two, would require us to lose 1 gigabit port to get more PCIe lanes onto which we'd then be able to connect our boot drive. But again, and I can't stress this enough, we're making a router and hard drive performance isn't really that important, so using a PCIe lane of any generation would be a waste. We haven't come to a final decision yet. We're talking with a couple of companies that are more experienced in designing embedded systems as to what they think and how they would approach this issue. And we hope the verdict will be out in a week or so. So make sure to subscribe, as I'll report on the final decision in the next month's update. And since we're talking about PCIe lanes, we also did a whole lot more investigation into Wi-Fi standards and discovered that PCIe 1x1 is simply not enough for anything but the very basic functionality / bandwidth. So we decided to swap out the initially planned M.2 key M connector, which is used for storage, for another M.2 key E1, into which we will then route PCIe by 3 lane that will allow us to support Wi-Fi cards with MIMO 2x2 streams that are much more performant compared to the 1x1 that is supported by the SDIO bus on the other M.2 connector. Whew, that was a long one. So why support 2 networking cards then? Well, because it turns out that the majority of home automation cards, also known as Tri-Radio, which stands for Wi-Fi, Bluetooth and Thread, don't really focus on high bandwidth all that much. In fact, most of them use the aforementioned SDIO bus for Wi-Fi traffic, which means it's pretty much impossible to find Wi-Fi cards that have high bandwidth Wi-Fi along with Bluetooth and Thread. So we figured, you know what, let's just put 2 M.2 connectors on the board, one specifically for high bandwidth Wi-Fi 6 on PCIe bus version 3, and one with Tri-Radio support for home automation on the SDIO bus. I'm happy, you're happy, everyone is happy. Let's now go over some less stressful stuff, the development boards. If you recall from the previous month, I explained that we purchased a couple of development boards that are manufactured by the company that makes the CPUs that we're going to use in our project. And these boards come with everything included to properly test all the functionalities and maybe more importantly, the performance of the CPU. Well, I'm happy to report that we're all up and running with these boards. Now, you probably think, why is that such a big deal? So let me explain. These boards obviously come with plenty of documentation, which unfortunately has several flaws. First, it's written for experts. If you're new to embedded systems, well, fuck you, figure it out. Not to mention that half of the commands don't even work because the documentation itself is several years old, but the tooling has moved forward, so they're often out of sync, so to speak. And even when you do manage to make it work, the application is so narrowly focused on that one board in particular that you can't help yourself much with the accumulated knowledge from the documentation. And God forbid to introduce or explain any kind of nuance. Nope, you're on your own. And NXP, the manufacturer of the CPU, seems especially bad with the documentation. It's all over the place. Some parts are on their website, but the URLs are structured poorly, so there is no way to navigate to a newer version of an article you found, even when you know for a fact that the newer version does exist. Then some documents are in PDFs that you download from the product page, and some they have on their blog website that are structured so poorly that they are a pain in the ass to even read through, let alone to follow them. And you know what adds insult to injury? The fact that you can find better documentation for these products elsewhere. Let me give you an example. When I was compiling U-Boot, which is a bootloader, more on that soon, I found documentation for exactly the same board on the U-Boot website. Documentation that is much clearer and better organized than the one that the board came with. Wait, I said I was going to talk about less stressful stuff, right? So here's the wins I achieved with the reference design board. This episode is brought to you by PCBway. I've been working with them on my custom keyboard project and I was super impressed with their speed, quality and price, so I'm more than happy to recommend them to anyone who needs any kind of PCB manufacturing done, whether it's just for a couple of prototypes or if you need a larger production run. Link to their website, of course, down in the description. Back to the video. I successfully managed to build both the first and the second stage bootloaders, none of which were provided by NXP, by the way. Then I flashed the NOR chips with them and the device successfully entered into U-Boot. By the way, if you don't know what I just said, don't worry, let me explain like I'm 5. When the CPU powers on, it has a tiny bit of code stored within itself that tells it to look into a particular pin on what to do next. This piece of tiny code is called primary bootloader and the place it's stored at is called internal ROM. The pin I'm referring to is then connected to what is called a NOR flash, and at the very start of the flash chip is stored something called bootloader 2 or BL2. This bootloader is also very tiny and is basically responsible for telling the CPU where and how to turn on access to memory, and in our particular case, how to configure SerDes lanes, because each of them can be configured either as a networking port, a PCIe lane, or a SATA bus. Once bootloader 2 is done, it then passes control to bootloader 3, which is often written as 31, because bootloader 3 can also have several stages. But for the purpose of this video, we're only interested in U-Boot as a whole, which is the first environment that you can actually interact with. Think of it as a simplified command line only BIOS in your regular PC world. Here, networking already works, for example, not all the features mind you, but just enough that you can access outside network, and we'll get to why that is important shortly. If we look at the booting process as a whole, then bootloader 3's main responsibility is to load the Linux kernel into memory and finally run it, which brings us to another win. Because U-Boot can pass parameters to the kernel that's being booted and said kernel has network file system support built in, we can easily mount a network drive as a boot drive, which from development perspective is a huge time saver. Let me explain why. Imagine that for every change to any file, you'd have to manually copy it from your development PC to the device to test if it's working there. Well, it would take a lot of time. But if we mount a directory from our development PC into the board, then we can much more efficiently work on the files on our PC and just restart any service that depend on that file when we change them. By the way, if you'd like to see all this in a more hands-on / tutorial videos, let me know and I'll prepare a couple. I think there's a lot to learn here. Anyway, the good news here is that the root file system isn't the only thing that we can mount remotely. We can do exactly the same thing with the Linux kernel. Let me briefly explain, because most people don't know how embedded Linux works in this regard. You see, Linux kernel is an executable file. File in air quotes here, because it exists as a file in the traditional sense, just on the machine on which it was compiled. But on the device that it needs to run on, it only needs to live where it will be executed, in RAM. So what I can do when booting the device is inside the U-Boot bootloader, I can simply download it directly into RAM and run it from there. And it will live there for as long as the device is turned on. Obviously, if we want the device to boot without it being connected to any network whatsoever, then of course kernel needs to be somewhere locally, and that place is usually NOR flash, I mentioned earlier. These are very fast chips, but on the flip side, very limited in the amount of data they can hold. But the upside is they're super reliable and super durable, and given that the kernel image doesn't need to change often on an embedded device, are the perfect candidate. And I've succeeded in this as well. The official documentation for the board itself says that the last partition is dedicated to a fit image. And fit image is a file that combines Linux kernel with something that is called a device tree. Device tree is a relatively simple file that describes how devices on the board are connected to the CPU, what capabilities they have, and how to talk to them. Devices in this case are pretty much all the chips that are relevant to the operating system, such as NOR flash chips where our bootloader is stored, NAND flash chips for the OS file system, PHY chips for networking, and so on and so forth. You know how I mentioned earlier that U-boot, our bootloader, can access the network despite the fact that it's not an actual operating system? Well, this is how. Because we compile the bootloader itself with the device tree included, it knows how to talk to the PHY chips that are on the board just well enough that they can reach the network. And yes, for the keen-eyed among you, the device tree is used both in the bootloader and in the Linux kernel. So, to recap, we've successfully built a custom U-boot bootloader for the device and written it to NOR flash so that it became a permanent bootloader. Then we built a custom kernel which we can both load and run through the network as well as directly from the same NOR flash chip that the U-boot is on. And finally, we've built not one but several root file systems for different Linux distributions and tested all of them, both by being mounted through the network file system as well as loaded directly onto the 512 megabytes of NAND flash that the device ships with. And here I need to give a huge shout out to a company called Bootlin, to which I'll leave a link in the description down below. They didn't sponsor this video, nor are they even aware I exist, but they do provide training services for this kind of work, and more importantly, open source the documentation that they use for this training. And I must admit, I found a ton of value, so if you're into this kind of stuff, but don't know where to begin, there. Okay, now before we wrap this up, also a short update about logistics. There's currently 4 of us working on the project, so me and Aljaž full-time, plus Ken, which I've introduced in one of the previous videos, and another person who wants to remain anonymous for the time being. These 2 are working 1 to 2 days per week, which brings the total cost of manpower and services we use to around 15 to 20,000 euros per month. If we stick to this kind of burn rate until the end of the year, and provided we have a prototype ready by early last quarter, I believe we'll have plenty of runway left for us to successfully raise a seed round. Because, well, as I already explained in my previous videos, 300,000 is simply not enough to bring a device of this class to market. Oh, and one more thing, we saved some money because a company called Ani, who are friends of the channel, have provided me with a beast of a PC that compiles the Linux kernel in absolutely no time. I've done a build video on that, but haven't had the time to edit it yet, so be on the lookout in the next couple of weeks. But for now, Tomasz from Slovenia, signing out.